Okay, so now we're going to shift our focus to robotics looking into the ocean, particularly autonomous science in support of oceanographic science. And our speaker is going to be Mike Jakuba. He's a research engineer at Woods Hole Oceanographic. Mike got his PhD in engineering from MIT Woods Hole Joint Program. Actually, a lot of his work was with the autonomous Benthic Explorer, one of the first real AUVs for ocean science, working on nested survey strategies for discovering hydrothermal vents. After that, he moved on to get a postdoc at Johns Hopkins University, where he did a lot of the control work for the Nereus Hybrid remotely operated vehicle. That's an 11,000 meter vehicle. And then he went on to the Australian Centre for Field Robotics, where he worked with a really great group down there that's doing a lot of work in classification and image processing. I think brings some really unique perspectives, and also kind of working on more shallow robotic systems as opposed to the deep systems we often do at Woods Hole. And he came back to Woods Hole, I guess, about 2 years ago now. He's been working on a variety of projects, and today he's going to be speaking to us really about autonomy robotics for oceanographic science and how we use that autonomy in ocean sciences, but really driven by the needs of ocean sciences. So I'm going to turn it over to Mike, and look forward to your talk.
Thank you, James. And you will certainly see that my talk is colored by the experiences that James just mentioned. But in any case, just wanted to go over sort of my objectives. I wanted to provide an overview of the state of the art through some case studies. It is by no means comprehensive, so I apologize in advance if your favorite study is not in here. Provide a definition of autonomy and delineate its forms as implemented in practice, because there are several different ways that researchers have developed autonomous behaviors in systems. And identify the characteristics of oceanographic science questions that have benefited from autonomy, with the ultimate objective, I guess, particularly for me, is to understand what forms of autonomy are pertinent to illuminating aspects of the carbon cycle. So the traditional definition of autonomy is this sort of perception, decision, and action loop. And perception starts at the very basic level of just simply sensing, logging, processing, moving up into clustering, things that start to add semantic meaning to the data that's coming from. Classification, mapping, predicting forward where your data might, what your data might predict about the rest of the environment. That moves into a decision phase, which at the very basic could be reactive, simply responding to an instantaneous measurement based on heuristics. More rigorous techniques involving optimization, multi-objective optimizations, perhaps including things like state of the vehicle itself, not just the data you're sensing. And then, of course, the action. And the action space is growing, actually. So now with multiple vehicles, we're talking about when should we deploy vehicles versus recover them. Certainly the trajectory, speed, where the vehicle is going to go. Sampling parameters are becoming more and more important as well. So a lot of instrumentation is now becoming quite sophisticated. And in fact, links back in with trajectory. So if you've got a mass spectrometer, for example, that needs to do a full spectrum scan, it doesn't make sense to drive a kilometer while it's doing that if you're interested in sampling the water in one place. And then finally, and this is still off in the future, actually intervening with objects on the seafloor and the water column and so on. Wanted to also add sort of what I mean by oceanographic science. We've been talking a lot about physical oceanography, but I'm based on my sort of biases, having started working with the autonomous Benthic Explorer, physical oceanography, biological oceanography, chemical oceanography, but also geology, since we do a lot of work on the seafloor. Automatic versus autonomous. I think this quote goes back originally to Jim Bellingham, talking about how these vehicles have been really more automatic than autonomous, but I think that's a shifting baseline too. Here's how I'm defining it for the purposes of this talk. So what I regard as kind of automatic vehicle systems, reliability, dynamics of control, behaviors, mission primitives, navigation, including SLAM, which at one point was considered the holy grail of autonomy, but now is largely a solved problem in some circles anyway. Path planning, fault detection and tolerance, multi-vehicle formation control, communication technologies, compression technologies, and the development of instrumentation. All of these do certainly feed into aspects of autonomy. Certainly persistence, a lot of these things are involved in persistence. But for the purposes of this talk, autonomy, the cutting edge, I think, is represented by model-driven adaptive sampling, model-based feature detection and classification, online learning, semi-supervised learning, and the deployment now of deliberative planners that can actually optimize between different objectives. and change the mission on the fly. I did a literature search. Here's my criterion. I think this unfortunately undersampled a little bit of the AOSN literature, but in any case, this is what things look like since 1990 that involve autonomous underwater vehicles. A large number of scientific results. I'll have the temporal perspective in a second. Technical advances related to the items on the left that I showed you before. Autonomy, certainly more recent publications, and then still a large number of papers involved in basically vehicle designs and sort of lower aspects or lower level aspects of vehicle design and control. Here's how those publications look like versus time. So we've been talking about technical advances since the mid-90s. There are some earlier AUVs, but those didn't show up in this. Autonomy about then as well. But scientific results really only started in the late 90s, and it's perhaps notable that we're starting to see actually scientific results from AUVs start to increase in number over the papers discussing just their technical aspects. Papers using advanced autonomy with scientific results, that's very nascent. It's just starting, but I think it's about to explode, and there's still, of course, a fair number of in that other category. All right, so let's break down the autonomous ocean science. Again, I think AOSN is a little bit underrepresented here, but really I found 15 papers through that. Onboard autonomy probably has the longest history. And that reflects in some respects the fact that it used to be we ran around with just one vehicle and we couldn't communicate with it. Applications, plume tracing, animal tracking, hydrothermal exploration, the DepthX vehicle, which was attempted to take targeted samples based on its own interpretation of the cenotes that it was deployed in. Triggered sampling, in particular in nephloid layers, Deepwater Horizon, thermocline tracking and oceanfront tracking, more modern. Examples of onboard autonomy, offboard centralized autonomy, autonomous ocean sampling networks driven by uncertainties in models. Coordination of glider fleets is another big one, driven there by the fact that the gliders themselves don't have the computational capability to really perform the autonomy online. And then co-robotic methodologies, which I think are, particularly in my field where we work with a lot of deep diving robots in sort of expeditionary science, are going to start to be very important. And I'll give some examples from Deepwater Horizon in particular. But I wanted to start off with actually the work that I was involved in Australia. This is the integrated marine observing system as deployed in Australia. It includes a number of facilities that are coordinated to varying degrees. I was a part of the autonomous underwater vehicle facility, and probably our main scientific contribution was the the repeated survey of these benthic reference sites. Basically, the idea was to look at the very same spots on the seafloor year to year in these places highlighted in the boxes along both the eastern and western coasts of Australia, with the idea being that as the currents along the eastern and western coast are expected to strengthen, they will bring more warm water down, and the benthos will act as an integrator over time, and we should start to see ecological changes in those reference sites. Now, the key thing there was to be able to image exactly the same portions of the sea floor, and I think this represents pretty much still the state of the art in terms of vehicles that are, sort of the very cusp of as automatic as you can get before you get into sort of autonomy that involves perception and mission and knowledge of the overall mission. The ACFR underwater survey pipeline starts with visual feature registration, leading into using SLAM for navigation, in post-processing at this point, and finally visually consistent 3D reconstructions. These are 25 by 25 meter sections. 3 of these were produced in each one of those squares. It's done every year. There's a whole lot of literature devoted to getting through this whole pipeline. And also the sort of value of this type of representation. They're three-dimensional, you can spin them around. It's a great tool for exploration of the data set. And it has started to yield actual scientific results. So this is an example of resolving benthic change, literally looking at the same rock from year to year, some kind of Gorgonian, I think, has grown here. In this case, this is off the western coast of Australia, where a high temperature event was experienced at some point during the year, and evidence of chloral bleaching is quite clear between the 2 years. So again, I think that's kind of the state of the art in terms of before we get into really autonomy that has knowledge of what one is trying to achieve. Okay, so statistical power of the data set from that type of science depends on precise revisitation and high resolution. There's really little need for real-time perceptual autonomy. You can still pre-program the missions, but you are relying on a lot of recent robotics advantages. The challenges are in handling the data volume, and in fact, there's a lot of automated processing, and in particular, processing devoted to gathering semantic meaning from those images. The old technique of employing an army of graduate students to sift through those images is not really viable when each one of those boxes represents tens of thousands of images. And there are opportunities, too, in terms of doing science knowledge discovery. As these data sets become large enough, you can start to mine them. All right, case study 2. So then we get into a little bit more of the autonomy, or mission cognizant autonomy. Geophysical plume studies with AUVs, in particular ABE and Sentry. These are vehicles that I've worked with extensively. This was a technique pioneered by Chris German to use an AUV to help localize hydrothermal vents on the seafloor. Basic idea was you start up in the neutrally buoyant plume found by CTDs, cast usually first, identify places where buoyant plumes were intersecting that plume, do a survey at a sort of mid-height to gather the geological context, and identify, at that point, localized anomalies, finally drop down to the seafloor, and do a photo survey providing a preliminary classification of what biota was down there. So the opportunity for autonomy in here is in improving synopticity, lowering the cost, since originally each of these surveys was done independently, vehicle recovered, data analyzed, new mission planned. If the vehicle could do these all on its own, that would save quite a bit of time. So increasing the scientific yield and improving the efficiency. The challenges are identifying the feature of interest in the sensor data, and of course responding appropriately to the contact with that feature. There's also the very practical issue of data integrity and sensor failure. And there's also, in at least my field, somewhat of a risk aversion in expeditionary science to employing autonomy. These are grants that are relying on existing technology to achieve their objectives, and there may be some resistance to possibly compromising that. So a modest early success back in 2004 was the use of ABE and a clustering algorithm used on the near bottom surfaces that basically aggregated lists of the highest temperatures and redox potential readings that it received, clustered them into groups, ranked those clusters, and ultimately drove back to the highest ranked clusters and got additional data there. And in this case, about 36% of the high value images in terms of classifying the biota there were derived from that autonomously chosen survey. And this kind of method is good in that risk-averse environment where you guarantee a minimum data set of the original track lines, and it's appropriate when the feature signal is qualitatively reasonably well known, but you can't also just define a trigger level when you might want to immediately change your trajectory. Rapid event response, in this case I'm going to talk about Deepwater Horizon, is another example where we're talking about surveying a plume, but it poses additional challenges. We had an unknown signature in this case for the plume that we were looking for, a very limited development time, and so that's a very practical concern in the sense that, well, we don't have necessarily the time to develop the autonomy nor the data up front to understand what we're actually going to be looking for. But as opposed to back in 2004, the maturity of acoustic communication, especially with these deep diving vehicles, permits a co-robotic approach. The basic goal was to follow up on these various reports about the possible existence of a subsurface plume at somewhere around 1,000 meters. The subsea assets we had involved, AV Sentry, a cabled CTD with water sampler, both equipped with a Tethys mass spectrometer, which is one of those sort of more modern instruments that's multimodal and that can change how it samples depending on what you're trying to achieve. Real-time visualization, absolutely key to any kind of co-robotic approach. In this case, we were telemetering up data from the Tethys instrument in particular, as well as other instruments on the vehicle, and plotting them in real time along with currents from the ship and so forth. And that was helping us decide where to put our assets next. In this case, you can see the sort of plume here is in the black. This is the first Sentry mission, and this is a second Sentry mission after we'd already found the plume. So a kind of storyboard, vertical cast confirmed the existence of the plume with this circular track around the site. We conducted Sentry 64 in a completely pre-planned fashion with the hope that we would be able to, or would be bold enough to cut off these edges when we knew we were outside of the plume, but we decided that things were going well and we wouldn't do it. Same plan for Sentry 65, except that instead of having that opportunity, we actually lost track of the plume in the telemeter data. So we were able to retask the vehicle acoustically, refine the plume, and continue the survey for another several kilometers, which was fortunate because immediately after that vehicle was recovered, weather rolled in and that was our last chance. So we got a few extra kilometers out of stability. But that's a pretty primitive approach to co-robotics. This is again the plume, in this case identified by just a static threshold computed after the fact. So the question is, with all these sensors on the vehicle, but an unknown signature for the plume ahead of time, is there an opportunity here for co-robotic feature detection, which is something I'm particularly excited about? So the basic idea would be to take sensors, pre-process them in reasonable ways, cluster them to generate, for example, in the particular approach I'm taking here, a Gaussian mixture model, telemeter those model parameters up to human operators that would provide semantic labels, which could then be fed into an adaptive planner and ultimately into the control system to tell the vehicle when to turn around, go back into the plume, that it's past the plume, and allow it to use that Gaussian mixture model to further classify readings that it gets ahead. So there was a large list of chemical sensors that I used there. I'm just going to go through two of them. We actually got pretty good results with using all of them. But so here's optical backscatter on one axis, methane on the other axis, and time on this axis. The clustering algorithm here uses a projection of that without time. So we're ignoring the fact that these are time series, and that definitely results in somewhat reduced performance than if we included that, but it's preliminary. So you can see we used a particular means of identifying a Gaussian mixture model, the variational Dirichlet process that doesn't require a priori knowledge of the number of clusters, which turned out to be very valuable. Trained on just this portion of the data, it identified 3 clusters. The green is the plume. The red, which doesn't show up in the optical backscatter signal, is actually the decay of the mass spectrometer. And then there's this data here, which seems to be of somewhat uncorrelated with the methane. And in fact, the algorithm also gives you a measure of how likely that data is and suggests that something weird is going on here. Trained on here as you can see, the cluster is just projected in 2D, but I'll move forward since I want to get to a couple other things. Trained on the whole data set, the algorithm actually does a pretty decent job of identifying this as something unique as well, and in this case, probably some kind of sensor failure. And so that's the case where you've got to be careful about the techniques you choose when it comes to co-robotics, because you do want any kind of data processing that happens subsea has got to be ready to handle things that you don't expect and alert you to that. In any case, that was able to produce once semantic meanings were applied by humans, a similar model of the plume as the straight threshold. This was done in post-processing. We didn't do this in real time. So in conclusion, autonomy introduces risk into expeditionary science, and that's something we need to trade off. Co-robotics has the potential to reduce the need for precise descriptions of features or training data by virtue of communication, but communication and visualization are critical enablers, and machine learning methods probably have the highest potential for yielding that dimensionality reduction that's necessary to use the limited communication channels effectively, be they acoustics in the case of the deep diving AUVs or just periodic surfacings. Case study 3, ephemeral localized oceanographic features. This is now not my work, so I'll be very brief on this, but certainly notable successes in the last few years using autonomy have been in tracking ocean fronts, tracking and sampling in intermediate nepheloid layers and other biological hotspots, patchy phenomena. The challenges here are actually somewhat similar: feature description and detection, acquiring the best samples. When do you fire your water samples, for example? And high-level goal specification and flexible mission planning are starting to become realities that allow people to specify these missions at a higher level. A lot of this work has used the Dorado AUV from MBARI and the gulpers, which are large capacity water samplers, the idea being that you want water samples from these, for example, intermediate nepheloid layers, which are spatially localized, and you want the best samples you can get. There's one example from Zhang et al. Of dealing with the fact that you don't necessarily know the threshold ahead of time by essentially locally determining what threshold is relevant by passing through your layer once, deciding where the peak is, then sampling hopefully on the next pass if it meets certain criteria, or if not, on the third. Flexible mission execution, using a mission executive called T-Rex developed at MBARI. This is a survey of a volume where basically the operator specified that they wanted to take samples and map the suspected intermediate nepheloid layer within this area, but gave the vehicle very little information about what it was supposed to do beyond that. And if you look closely, you can see the vehicle is actually modulating how densely it was sampling in response to the data that it was getting and where it fired the gulpers. All right, so onboard autonomy is essentially required for ephemeral or highly localized features, but good results still require good feature descriptions. Those can be sometimes intuition or detailed knowledge of the phenomenon, or training from lots of classified data. That training is often hard. Getting that data is often hard. And that's where Co-Robotics, I think, has a role to play. Triggering an adaptation inevitably implies trade-offs. So frameworks for handling those trade-offs are nascent, though, in the AUV community, and we'll see more of that. Very briefly, AOSN, I think there's going to be a lot more on this in the next talk, so I didn't want to get into too much detail, but the idea of coordinating a large number of assets using, the essential idea is to coordinate a large number of assets to reduce error in ocean predictions by driving the sampling program through the use of data assimilation into a model. That feedback loop is still here, and autonomy of all the types I've talked about moves towards increasing efficiency, be it onboard autonomy, so you don't have to direct vehicles independently, or formation control, for example, or error statistics-driven sampling plans. So, in conclusion, off-board centralized autonomy appropriate when, this is AOSN, when they're computationally intensive, global general circulation model-driven sampling. The greatest benefits, as Bellingham and Curtin pointed out, are derived from placing slow-moving assets advantageously relative to features of interests. Onboard and co-robotic autonomy are increasingly valuable and also viable. They will allow for higher level goal specification, reducing the decision-making burden on humans, and to incorporate studies of sub-resolution phenomena that aren't resolved in the GCMs necessarily, but that are important, but it's important to understand them within the context of the larger scales. I think a big question here is how well do these kinds of ideas extend to global scales? Do we have the vehicles that will behave in the same way? All right. In summary, onboard autonomy, triggered sampling of ephemeral features, extremely small spatial scales or temporal scales. Off-board centralized autonomy when there are computational limitations involved, when you have multiple scales, many mobile assets, and integration with remote sensing or models. Multiple objectives, large distributed research teams are all applications when you really need a lot of computational power. Co-robotics applies especially in exploration, when the mission objectives are evolving, when the features of interest are poorly characterized and you have to learn them on the fly, and in a more practical sense in rapid response characteristics when you simply don't have the time to develop specialized algorithms. So in conclusion, AUVs are routinely delivering new oceanographic science, and that technology is mature. Autonomy is also beginning to deliver new oceanographic science results in certain applications. So the big uncertainties concerning the carbon cycle, do they share the characteristics of the applications that I talked about in this case? I think that's a question that I'll be certainly thinking about a lot over the week. Thank you.